Welcome to this video on types of precision sensors and their applications. In precision engineering, accurate measurements are critical. In this video, we'll explore the key types of sensors, how they work, and where they're used in the field. Let's start with why sensors are so important. In precision engineering, sensors act as the eyes and ears of a control system. They provide the real-time data that drives high-performance control loops, ensuring accurate positioning, force control, and more. Without precise measurements, precision engineering wouldn't be possible. Precision sensors can be grouped into several categories, each designed to measure specific physical quantities. Displacement and position sensors track linear or angular movements. Velocity sensors monitor motion speed and direction. Force and torque sensors measure mechanical loads, while environmental sensors keep track of temperature, humidity, and other conditions. Understanding these categories helps in selecting the right sensor for each precision application. Capacitive sensors are known for their high-resolution measurements in precision engineering. They operate by detecting changes in capacitance between a probe and a conductive target, allowing them to measure displacement with nanometer-level accuracy. These sensors are widely used in semiconductor wafer alignment, precision stages, and metrology tools, where even the smallest deviation can impact performance. Inductive sensors operate based on the principle of electromagnetic induction. They detect changes in inductance caused by the presence of a metallic target, making them ideal for robust, non-contact displacement measurements. Inductive sensors are widely used in machine tool monitoring, spindle positioning, and applications requiring reliable performance in harsh environments. Optical encoders are key components for measuring rotary or linear motion with high precision. They work by shining light through a patterned disk or scale and detecting changes in light patterns as the disk moves. This allows them to provide accurate feedback on position and speed, making them essential in robotics, precision stages, and automated inspection systems. Laser interferometers provide the highest level of measurement precision in many applications. They work by splitting a laser beam and measuring changes in phase when the beams are recombined. This allows them to measure displacement down to fractions of a nanometer. These sensors are essential in coordinate measuring machines, wafer steppers, and other applications where nanometer-level precision is required. Piezoelectric sensors generate an electrical charge in response to mechanical stress, making them ideal for measuring dynamic forces, vibrations, and pressure changes. They are highly sensitive and capable of capturing rapid changes in mechanical loads. This makes them indispensable in applications such as structural health monitoring, precision balancing, and high-frequency vibration analysis. Precision sensors play a vital role across many high-tech industries. In semiconductor manufacturing, they ensure wafer alignment and process control down to the nanometer. In metrology and inspection, they provide accurate 3D measurements of critical components. Aerospace uses them for structural health monitoring, while precision robotics relies on them for reliable positioning. Each sensor technology finds its place in pushing the limits of performance and innovation. Choosing the right sensor for your application is crucial to achieving optimal performance in precision systems. Always start by defining the measurement requirements such as resolution, bandwidth, and range. Consider environmental factors like temperature, vibration, and electromagnetic noise. Evaluate the sensor's integration capabilities and calibration needs. By balancing these factors, you can ensure your sensor selection matches the performance demands of your system. Precision sensors, while powerful, face challenges that must be addressed in system design. Thermal drift can impact measurement stability, while electromagnetic interference and noise can distort signals. Proper mechanical mounting and alignment are essential to maintain sensor accuracy. Understanding and mitigating these challenges ensures that sensors perform reliably in demanding precision engineering applications. In summary, precision sensors are the backbone of modern control systems. They enable accurate measurements that are vital for high-performance applications in semiconductor manufacturing, aerospace, robotics, and metrology. Understanding sensor types, their challenges, and best practices ensures you choose the right sensor for your application and achieve reliable, precise performance. Keep learning and stay updated with emerging trends to maintain a competitive edge in precision engineering.